Welcome to clickmateprojects.com. Here we are going to discuss about an efficient and effective analytical placer for FPGAs. Field programmable gate arrays provides fast and riskless means of realization of digital circuits. The digital logic elements need to be allocated places in the prefabricated logic blocks of FPGA. The interconnections of elements can be programmed by the designer to achieve any functionality with a desired performance. Hence, the placement of logic blocks in the FPGA is a predominant step in achieving better performance of FPGA-based systems. Other way speaking, the quality of placement in FPGA determines the quality of the system. Hence, there have been significant research efforts in development of efficient placement techniques in past few decades. The FPGA placement optimization has been carried out by several methods like minimum cut, quadratic, simulated analytic, genetic algorithm, and particle swarm optimization. The min cut techniques uses recursive partitioning to divide a netlist of circuits into increasingly smaller subcircuits. In this technique, the solution may vary depending on the partitioning and it does not reach a goal of solution. The quadratic algorithm attempts to minimize total square length, though it is faster compared to other techniques, but it cannot consider both timing and wiring length. For optimization, the simulated analytic is based on random movement of logic elements with a very robust cost function. It provides a global optimal solution to the problem but is speed limited. The evolutionary algorithm like genetic algorithm PSO have been always observed to converge to a global optimum as opposed to gradient based optimization schemes, those getting trapped in local optimum. These population-based schemes have been applied to solve the placement problems. Swarm intelligence have been applied for digital circuit placement in FPGA platform, where the PSO optimization algorithm have been used for optimized placement. Reinforcement learning and SVM are also used for placement and routing in 3D FPGAs. Here, discrete and continuous PSO is used for FPGA placement problem. In this work, the applications of different variants PSO like constructed PSO and time-varying inertia-weighted PSO to solve the FPGA placement problem as proposed. To our best knowledge, these efficient variants of PSO have been not applied to FPGA placements. Now I am going to explain the flow diagram of our project. In the first stage of our flow, we use the initialization points for the PSO optimization. In the PSO, it simulates the behavior of bird flocking. Suppose the following scenario: a group of birds are randomly searching food in an area. There is only one piece of food in the area being searched. All the birds do not know where the food is. So, what's the best strategy to find the food? The effective one is to follow the bird which is nearest to the food. PSO learned from the scenario and used it to solve the optimized problems. In the PSO, each single solution is a bird in the search space. We call it particle. All the particles have fitness values which are evaluated by the fitness functions to be optimized and have velocities with direct the flying of the particles. The particles fly through the problem space by following the current optimal particles. PSO is initializing with a group of random particles and then searches for optima by updating generations. In every iterations, Each particle is updated by following two best values. The first one is the best solution it has achieved so far. This value is called P-best. Another P-best value that is tracked by the particle swarm optimizer is the best value obtained so far by any particle in the population. This best value is the global best and called G-best. When the particle takes part of the population as its topology neighbors, the best value is the local best and it is called L-best. Here we check the each and every fitness values of the points regarding to the placement of the FPGA architecture. From the netlist file, it initializes the points and then these are arranged as a matrix. And according to the each and every fitness values in the particular area, these fitness values are captured, and if the fitness value is matching to the particular threshold ranges, and this was updated. For each and every fitness ranges, this was formed as a clusters. And finally, we analyze the placement details of our proposed design. Thus, we reduce the placement of FPGA architecture. Now I am going to explain the running procedure of our project. In this stage, we give the coding as main.m file. Now just run main.m file by right-click it and click run file. In the first stage, it gets the netlist file from our user. So open the datas and gives the netlist file. Here we are using MCNC circuits as a descriptive file. Then from this file, it collects the data of each and every point and rearranges it in an axis. These points are the initial values of the placement details for the given data, and after that, for each and every iterations, the placements are updated. The updated details will be displayed for each and every iterations in the figure 2. The figure 1 displays the initializations of our given data. Then after that, the best fitness selection, it will display the best fitness ranges of the area, and this optimized region was updated for each and every iterations. The iterated values and the best fitness values are displayed in the command window as in the running playback. Finally, according to the placement details, we extract the values which are related to the optimized wire length, the power flow, and then area consumption and critical path, that's delay effect. We can calculate it according to the placement details of the FPGA architecture. Because of the number of FPGA kits, that means the number of logical circuits will be at placements of arranged in the points. The updated particles will represent the updated informations of the placement details which are denoted to the best fitness ranges which are lead to placement. Then finally, this placement result will be updated, and the power value, critical path delay, and then wire length are extracted from the placement detail result. This will be checked for each and every iterations. The populations will be updated in the PSO as the seeds which are grown to the particular stage. The matching, if there was matching to the threshold ranges, this will be updated. From the updated result, this will be placed to the new area. And finally, the graphs according to the values will be displayed. Thus we optimize the placements of FPGA designs as from the netlist file. Thank you.